Section 2.9, Calculus of Hyperbolic Functions. So as a nice sideshow of all the things that we've seen on these applications, we run across something that is an application of exponential functions, and it's actually a combination of exponential functions. So we have something called the hyperbolic sine h, or some people say it, which is e to the x minus e to the negative x divided by 2, and cosine hyperbolic, or the hyperbolic cosine, which is e to the x plus e to the negative x over 2. Now, you can break any of these functions down in this table right here. You can break any of them down in terms of sine h, cosine h, and e's, okay, and derive these derivatives as well as the integral formulas. But for the most part, we really just need this chart, okay? So this kind of summarizes all of the derivative rules, okay? We have f of x in the left column, the derivative of f of x in the second column, and if you look at them, there are a lot of similarities. One noticeable thing is the derivative of sine is cosine, okay? Just throw an h in there, and that property still works, okay? Just as a heads up, sine and cosine and exponential functions, we will see in a few chapters, they are completely related, okay? They cannot be separated. They actually sometimes act the same. All right, so the derivative of cosine h is sine h. Okay, so there's a difference of a negative there. We've got tangent to secant squared. That one still works. Cotangent to cosecant sort of still works. We have a negative. Remember that negative sign there. Secant to secant tangent. Okay, the negative sign is there again. Cosecant, the hyperbolic cosecant, the derivative of that is cosecant cotangent, which is what it was before, except we have a negative sign there. So keep track of that. Now, as always, in every page there's a little link that's where you could get all this information, because this is OpenStax Calculus Volume 2. This one's covered up, but it's on the next page, so if you want that, keep track of that. And make sure you write these rules down. They will be very useful as we go. Alright, so let's find the derivative of hyperbolic sine of x squared. Okay, now we have to keep in mind, we have to worry about the u substitution, or our chain rule here. Okay, so the outside function is the sine, hyperbolic sine. So the derivative of that is the hyperbolic cosine of x squared times the derivative of our inside function, which is going to be 2x. Okay, so this is 2x hyperbolic cosine of x squared. Okay, same idea with this one, except now our inside function is the hyperbolic cosine. Alright, so our chain rule would say this is 2 times hyperbolic cosine x. I guess I don't really need to write that there, but those parentheses. Hyperbolic cosine of x to the first power times the derivative of hyperbolic cosine, which is hyperbolic sine x. Okay, next, derivative of tangent of x squared plus 3x. Okay, well, the outside function, the derivative of that is hyperbolic secant squared. We'll keep the inside function times the derivative of the inside function, which in this case is 2x plus 3. Next, we have the derivative of 1 over hyperbolic sine squared. Okay, now I wrote it this way because with the parentheses squared rather than with the 2 here, just to emphasize the fact that that is an inside function. Okay, we have a u substitution. So let's write this as the derivative of sine hx to the negative 2. In that case, the derivative, let me add parentheses there. In that case, the derivative will be cosine, hyperbolic cosine. We'll bring a negative 2 down. This is to the, actually we don't need that. I got a little ahead of myself. Hold on. We need to keep our inside function. So negative 2 hyperbolic sine to the negative 3 times the derivative, hyperbolic cosine. So this will end up being negative 2 hyperbolic cosine over hyperbolic sine cubed. Okay, next, briefly, we've got some integrals. U substitution along with recognizing things from that table is going to come in here. All right, so this one is x times hyperbolic cosine of x squared. Okay, now hopefully you notice that there is an inside function. That inside function is x squared. So in this case, we will make du equal to 2x dx. Now, we need to replace an x dx. So we'll need to divide by 2 there. So 1/2 du equals x dx. So now we can replace everything in this integral. I'm going to bring that 1/2 out. Integral of u. So we have cosine h u du. Well, the integral of cosine is going to be sine of u, and we'll have our 1/2. And of course, we want to write this as hyperbolic sine of x squared plus c. This is an indefinite integral, so we need to make sure we have plus c. Okay, next we have the hyperbolic tangent. Okay, so what are our properties? I didn't talk about this one, but tangent is still sine over cosine. So since we don't have a direct way to get the integral of tangent, we'll first break this into the integral of sine hx over cosine hyperbolic of x. Okay. And while we could try doing u substitution of sine, because sine, derivative of sine is cosine, we then have our du in the denominator, and that wouldn't work too well. So I'm going to go with cosine of x. So du is sine h of x dx. So this actually transforms into 1 du, okay, just du, is 1 over u. So 1 over u du, which the integral is ln of the absolute value of u, which would then be the natural log absolute value of cosine hx plus c. When you first start out with that, it doesn't look like that's the direction you're going to go, but in fact you do. Okay, number 61. U substitution will be very handy here because we have an inside function, sine cubed, and the derivative of that is cosine. So we can make u sine hx. Du is then cosine hx dx. So this becomes the integral of u cubed times du, which is u to the 4th over 4 plus c. And since we know what u is, this will be sine h to the 4th of x over 4 plus c. Okay, next. Last integral of this form we're going to have, kind of flying through this, is hyperbolic secant. Alright, so first we should notice we have an inside function, first of all, that is 3x, which would make du 3 dx, or 1/3 du equals dx. So writing this in terms of u, we get the integral of secant, hyperbolic secant squared u du, and I'll bring my factor of 1/3 there. All right, now I'm just fine with having a secant squared because the integral of secant squared is tangent. So this is 1/3 hyperbolic tangent of u, and I'm going to go ahead and substitute it back in because u is 3x plus c. I always need to make sure we adjust for that inside function we've got. Okay, and we're actually going to skip this one right here. This is a mistake. Okay, so those are our integrals and our derivatives of just plain sine and cosine, tangent, the hyperbolic versions of those. Okay, so the next thing we're going to look at is integrals and derivatives of inverse hyperbolic, sine, cosine, tangent. Okay, inverse trigonometric functions in this way. Alright, so again, just like the first time we talked about trigonometric and the inverse functions, we're really just going to follow these patterns. Follow them. Okay, I've actually got two charts between here and the next page. So make sure you find which one fits and then use the one that applies. Okay, so I left that there for a second. There is our OpenStax website if you want to download these materials. And here are the integral formulas. Now, one thing to notice is that there's one of these that has two antiderivatives. This one right here has two antiderivatives. So there's tangent inverse, hyperbolic tangent inverse, and cotangent hyperbolic inverse. Okay, and that depends on the size. It depends on the size of our u. If it's less than 1, the absolute value is less than 1, or the absolute value is greater than 1. Okay, so we'll see that as we need it. Okay, so get your chart handy from that last page as we look at the derivatives first. Okay, so the derivative of hyperbolic sine inverse of x over 3. Okay, I want to make note that I have u is x over 3. Alright, so my du is 1/3 dx. Alright, so when I take care of this, okay, I'm going to have a 1/3 factor hanging around. Alright, so that is sine inverse. So that is going to be 1 over 1 plus u squared. 1 plus u, which is x over 3 squared. Okay. Wait, hold on. Oh, I left off square root. There we go. 1 plus that. Now I also have this factor of 1/3 because of the chain rule. I'm taking the derivative of that x over 3. So let me write that a little better. 1 over 3 square root of 1 plus x squared over 9. Okay, that is my derivative. All right, next for hyperbolic tangent inverse. Okay, this one, we notice we have a chain rule as well, except the inside function is the inverse tangent. So this will be 2 inverse, hyperbolic inverse, okay, to the first power, okay, times the derivative of the hyperbolic tangent inverse. So tangent is 1 over 1 minus x squared. 1 over 1 minus x squared. Okay, and the best way to write that is probably just as one fraction, or 1 minus x squared. So if you see an integral like something like this where you have one that has its own derivative, a chain rule might be necessary. Okay, next, hyperbolic cosine inverse. Okay, now we'll have to make sure we take the derivative of that 3x as we go. Alright, so the derivative of hyperbolic cosine inverse is 1 over square root of u squared. So this will be 3x squared minus 1 times the derivative of that inside function, which is 3. So let's make that 3 over the square root of 9x squared minus 1. Alright, hyperbolic cotangent inverse. Okay, now notice that's actually the inside function there. So let's use the chain rule first. 3 hyperbolic inverse cotangent squared times the derivative of the hyperbolic cotangent inverse, which is 1 over 1 minus x squared, the same as the inverse tangent. So I'm going to go ahead and write that here. Okay, over 1 minus x squared. Alright, now for some integrals. A few of these. Alright, so we need to recognize what is our inside function here. Okay, what's being squared in this case? So I can write this as u is 2x. Okay, and my du is then 2 dx, or 1/2 du equals dx. So when I work this out, I'm going to have a factor of 1/2 in here. Okay, let me write this as 1 over the square root of u squared minus 1 dx, du. Now, based on those formulas, that should be hyperbolic cosine inverse. Cosine hyperbolic inverse of u, which is 2x. And of course, because of this 1/2 we had here, well, really because of the 2x, we get a factor of 1/2 out here. So 1/2 hyperbolic cosine inverse of 2x plus c. Alright, 69 is a repeat. Look at that. Free one. Number 70. Okay. Well, the thing that's being squared right here is a 3x. Alright, so let's say u equals 3x, which makes du 3 dx, or 1/3 du equals dx. Okay. Now we have a small problem. We have this 2x hanging out here. So what we're going to do is take this 3x term, multiply it by something to make it equal to 2x. Okay, so I'm going to divide by 3 first. So that's 1/3 u equals x. And then multiply by 2, which means 2/3 u equals 2x. Alright, so I'm going to replace this with a 2/3 u. Okay, or equivalently, that is going to be a 3 over 2. Let me erase that. It's going to be a 3 over 2 because it's in the denominator. Now I'm also going to have a factor of 1/3. Okay, and that is 1 over u, square root of 1 minus u squared, du. Alright, now, ignoring the signs out front there, okay, then this is going to be a 1/2, hold on, it's the secant hyperbolic inverse, okay, negative, there we go, it's going to be a negative 1/2 hyperbolic secant inverse of the absolute value of u plus c. Okay, the 1/2 from our constants we factored out, and our adjustments there, and the negative because that's just in the rule. Now our u is 3x, the absolute value of 3x plus c. Okay. Okay, so the next one we've got, x squared minus 4. Okay, well, our u is x. Okay, and that is going to make, and we have an a of 4, or an a of 2. Alright, so this is going to be, once we take the integral, hyperbolic cosine of x over 2. Okay. Alright, next, what's being squared here? Well, how I could write this? I could write this as e to the x squared, so our u is e to the x, which makes our du e to the x dx. Okay, well, we've sort of got this redundant because our e to the x is actually a u, so I could also write this as du over u equals dx. Okay, so the way this is going to be written is 1 over u square root of 1 minus u squared du, which will be a negative secant, hyperbolic secant inverse, absolute value of u plus c and we box that way. Alright, which in turn leaves secant hyperbolic inverse absolute value of e to the x. Now e to the x is always positive, so I don't need those absolute value bars. I'm going to put that in parentheses though. Alright, last two that we've got. There's a couple of applications, and this is why this fits in this chapter. Assume that a hanging cable has the shape of 10 hyperbolic cosine x over 10 with x between negative 15 and 15, where x is measured in feet. And a hanging cable, like if you go to the movies or something like that, and you kind of have those hanging cables when you're in line, they actually do follow this pattern. Okay. Now we're being asked here to determine the length of the cable in feet. Now this is just arc length. Okay, so we can use our arc length formula from 2.4 and then the Pythagorean identity to work this out very nicely. Alright, let's go get some space. Alright, so the length, by definition, is the integral from negative 15 to 15, square root of 1 plus the derivative of cosine of 10 cosine h x over 10. Alright, so by our definition that we had earlier, that is cosine so that is going to be cosine h, the derivative of that function, because when you take the chain rule here, the 1/10 will actually cancel out the 10. So cosine, hyperbolic cosine squared, there we go, dx. Now, actually that's going to be a sine. Hyperbolic sine is the derivative of that. Alright, now our Pythagorean identity here is going to say this is going to become the square root of cosine, or hyperbolic cosine squared over 10, which is going to be square root of something squared, negative 15 to 15 of cosine. We're going to switch that in a second. Hyperbolic cosine squared of x over 10 dx. Okay, now the antiderivative of that is 10 hyperbolic sine x over 10, evaluated from negative 15 to 15, which is 42.586 feet, approximately. Of course, we'll have to